They actually own a ring light, so I'm like ready to be an influencer. Wait, that recorded? I'm leaving that in. I'm leaving that in. I don't care. I need a little whimsy in my life. Oh, okay. All right. Hi. Today I will be talking about the 2025 Nobel Prize in Physics, which went to John Clark, Michael or Michel H. Deveray, and John M. Martinez, and also some thoughts that I had on the 2024 prize that I didn't really share in the kind of rambly video that I did last year. So, preface on the Schrodinger's cat thought experiment. Something of a mascot of quantum mechanics nowadays, and originally a mockery of it. It was devised to show the absurdity of quantum effects at classical scales. How could a cat that is classical possibly be in quantum superposition or experience any quantum effects at all? Now, we can roughly understand this is due to a phenomenon called decoherence. All the quantum particles and atoms in the cat are constantly interacting with and measuring each other, and eventually they reach a sort of consensus, right? Well, if you take that cat to be so many electrons in a superconductor that you think they should be treated classically, and the quantum effects it should be able to experience to be quantum tunneling specifically, you get this year's Nobel Prize in Physics. Is that a terrible analogy? Probably, but I just wanted to include Schrodinger's cat, okay? I installed a German keyboard for this. Let me have this. So, first of all, I would like to take a moment to congratulate this year's Nobel laureates in physics, John Clark, Michel Deveray, and John Martinez. And not only in physics, but in other fields as well. I can only imagine how big of an accomplishment, how big of a win getting a Nobel Prize could feel like. And these people did, and they deserve it. So, these researchers have pioneered some really cool research and changed physics, or the world in the case of all the other fields along the way, right? And if you watch the Lecture on Physics this year, which I highly recommend you do because I'm not going through this alone, you'll know that behind the paper, which was awarded the Nobel Prize this year, are several improvements in detecting like really tiny voltages. And that's necessary because what's happening in the superconductor is basically on the level of trying to measure an individual quantum system's wave function, right? In fact, assuming I'm understanding all this correctly, that's exactly what it is, but I'm getting ahead of myself. So, if I had to sum up the research that won this year's Nobel Prize in Physics in one sentence, it'd go something like this. A current consisting of many electrons in a superconductor quantum tunnel, thus proving that quantum effects can appear at classical scales. Lots of words, let's get to what they mean. Quantum tunneling. There's really no way to explain this other than to link back to the analogy used by John Clark in his portion of the Nobel lecture this year. When you throw a ball at a wall, the ball bounces back. You may even know how to analyze this scenario physically if you remember some high school physics. What doesn't happen, however, is the ball passing straight through the wall, right? Without breaking it or somehow going above it if it's a hill or something, right? Now imagine instead, and yes, this analogy is sourced directly from the comment section of the Nobel lecture, that your neighbor is watching TV in their apartment and you can hear the sound of the TV coming um, from the sound of the TV from your apartment, right? The wall cannot stop the sound waves. And this is roughly what happens with the wave function of a particle. Particles don't have a definite boundary or a start and an end like a tennis or a billiard ball would. While the wave function isn't purely a mathematical construct, it isn't necessarily physical either, meaning it can sort of ignore boundaries like this. And because the probability that the particle is in any given location is given by this wave function, even though it may be very unlikely depending on how thick the barrier is, the particle could end up on the other side because, in a way, part of its wave function was already there, right? And taking this to the extreme, technically, an electron somewhere in my house right now could tunnel to yours the next instant. It's just exceedingly improbable. And also wouldn't really happen since, or wouldn't really matter since no information could be communicated, or else Einstein would be very unhappy. Um, so why doesn't your hand tunnel through the wall when you punch it after getting your ounce physics problem wildly incorrect? And yes, this is a self-call out. Well, other than the fact that it's extremely unlikely, well, because as I mentioned in the intro, your hand is like the classical cat. It's constantly interacting with so much stuff that any quantum effects kind of get smoothed out. As we will see, this is quite unlike what happens in the superconductor. In that scenario, the electrons interact with nothing but themselves because it's so cold. Anything else just doesn't have the temperature to get to them to interfere with their quantum effects. And this is also, to some extent, a property of the material being used because not all materials can be superconductors, technically. And this means that the electrons, or more accurately, Cooper pairs, we will also get to that, can start fusing their wave functions together, effectively creating one big quantum system at a classical scale. And this quantum system behaves just like any other. It can quantum tunnel. Like, isn't that just beautiful? This fact that after all the details of how the system got to this state have been abstracted out, the collection of Cooper pairs is just like any simple one electron quantum system. That's what's key to understanding this research, in my opinion, right? It's basically just this figure right here after we've applied the mathematical model of a quantum system to all of the electrons or all of the Cooper pairs in the superconductor. That's pretty neat. Um, so speaking of superconductors, the material, um, superconductors are materials with zero electrical resistance, and all superconductors require either really low temperatures or really high pressures, right? To be able to like superconduct, right? And you can think of this like electrons in the metal being so close together, so tightly packed that they don't really have anywhere else to go than forward. Since what causes electrical resistance in the first place is electrons bouncing off each other haphazardly, creating thermal energy, creating resistance, right? But if that cannot happen, then boom, you get superconductivity. As for why this cannot happen in a superconductor, right, all this haphazard bouncing around, that is because the electrons inside a superconductor are bound together into Cooper pairs. Um, the intuitive but classical, from what I can tell, explanation for this is as electrons move through the metal, the superconductor, the superconductor they attract nearby atoms, or more specifically ions, since that's what makes up metal, right? And eventually, other electrons will drift into these positive areas. This sets off almost like a chain reaction as these two electrons start getting closer. The sum of their effects on the nearby ions get stronger, and eventually they become bound into a Cooper pair. This only really happens at really cold temperatures, or really cool temperatures, pun intended. I saved it, Chad. However, it is important to note that the main direction of research with superconductors currently is looking into how to get them to be warmer, right? How to get them to function at warmer temperatures. So this might change soon. That's pretty cool. And while this aspect of superconductivity, I just explained it classically, it can actually be quantized using something called phonons, which behave like particles of vibration. And I'm not sure if I touched on this in the International Year of Quantum video, but in figuring out the quantization of light into photons, Einstein actually showed that photons must have momentum, which was the final push to let them be defined as not just waves, but also particles. So really, a lot of the things that behave as particles, um, it can be helpful to model them as waves and no, the other way around. A lot of things that behave as waves, it can be helpful to model them as particles, such as vibrations, right? And the reason phonons are modeled like this is because, well, first, well, they obviously have wave-like properties, right? They move through the material, like waves, as you can see here. They have an amplitude, for example. But they also act a bit like force particles, joining electrons together into Cooper pairs, and they're relatively quantized. One vibration, one of these phonons cannot join more than two electrons together because there just isn't enough attractive force to overcome the repulsion between the electrons. Phenomena such as this are called quasi-particles. Even though they're not fundamental particles themselves, it can be helpful in applying the larger framework we have for working with fundamental particles to various scenarios to model them as such, right? Even just look at this diagram right here. They're using a Feynman diagram from particle physics to describe the interactions between the electrons and phonons, right? This squiggle right here represents a boson, a force particle. That's neat. All right, getting back to Cooper pairs themselves, why do they matter for this macroscopic quantum effects thing? Well, there's this niche physicist, you probably don't know him. He came up with something called the Pauli exclusion principle. Did I do that sarcasm thing right? And you may know if you took chemistry, this principle means that two electrons with the same spin cannot occupy the same quantum state. The crucial thing, however, is that Cooper pairs are not electrons, they're pairs of electrons, which means they can occupy the same quantum state. The actual distinction here is between fermions with spin half and bosons with spin one, which Cooper pairs are because they consist of two fermions and the spins kind of get summed together. Uh, and because these pairs can occupy the same quantum state, they can condensate and become one big wave function. This is basically the process by which Bose-Einstein condensates form, actually, because all the bosons in a Bose-Einstein condensate are at their lowest energy level, they start exhibiting wave-like properties, or they kind of start behaving like their individual wave functions, all propagate to all of the other bosons in the Bose-Einstein condensate. They start behaving like one big quantum system. Um, yeah. So Bose-Einstein condensates also exhibit like these quantum properties at a macroscopic scale, and this year's Nobel laureates took this a step further and applied this to Josephson junctions and superconductors. Um, so here's a model of their setup, a superconducting wire with a so-called Josephson junction represented by a capacitor and a resistor. Um, what a Josephson junction like actually is a break in the wire with an insulating material so that no electrons can pass through there. And the reason this kind of model works is because the capacitor requires some amount of energy to be put in, representing the energy at which quantum tunneling effects first appear. So that's neat. Um, what this experiment tests is that what if something could pass through this junction? What if the entire wave functions, all of these combined condensed Cooper pairs, could tunnel through the junction, right? And in order to prove this, voltage would have to be observed in this wire. This is represented by the wording escape from a zero voltage state in the papers. And yes, I said papers. I would like to kind of discuss some of the more precise terms used in these papers because if you ever wanted to read them, I don't think my explanation alone would be adequate, or my explanation of superconductors and quantum tunneling alone would be adequate since there's a lot of language used. But yeah, as you can see, there's two papers, one from 1984 and one from 1985. The 1984 one really does a lot of similar things to the 1985 one, but it kind of develops the foundations which were needed to almost to like kind of definitively prove that quantum tunneling was happening in the 1985 paper, right? And please, of course, I can't like expect you to check these out yourself, but uh, I think these researchers deserve that, especially considering a lot of their experimental setup and a lot of the details of their experiment has been abstracted away by a lot of the news reporting. So I don't know. I'm not your mom. Do what you want. So as for how quantum tunneling is written in these papers, so you can identify that, it is an escape from a potential well. Basically, the particle wouldn't normally have enough energy to get out of this well right here, or actually this well as well. I'm so funny. Chat, I'm so funny. So yeah, it normally wouldn't have the energy to get to here, for example, but when they apply a microwave current or when they apply microwave radiation as um, as these experiments do, it suddenly can, right? It suddenly can overcome this well that it's in. So this probably isn't the visual you had in mind for a ball or a wave going through a wall, and that's partially my fault. However, the scenario is practically analogous. The Josephson junction through which the particle cannot classically pass through, not necessarily because it's an immovable object or approximated as such in the way that a wall might be when you were first studying collisions and kinematics, for example, but rather it does not have enough energy to force its way through, right? It's kind of like if you were trying to roll a ball up a hill, it would require a certain amount of energy at the start, or you would have to kick it with a certain force for it to go over the hill. Um, As I mentioned, this escape is achieved with the help of microwave radiation. And what really is investigated here is whether this collective particle, remember, actually condensate of all the Cooper pairs inside the setup, is quantized, right? The energy of this system is quantized because if it is, what one would see is that at specific frequencies of the microwave radiation, there would be a large increase in the escape rate, right? Um, so the particle would jump from this little energy to this little energy. And when it does that, the hill it has to get over becomes much smaller, but it can't, but if it were quantized, it couldn't like end up in the middle of this little level, and so there wouldn't be a continuous increase in the escape rate as the microwave's frequency gets bigger. And that is exactly what we see in this figure right here, right? We see this big jump, and then this big jump, and then this Smaller jump, still a jump. Yay. Um, uh, Yeah, so you might be asking, where does quantum tunneling come in then? Well, a similar setup was used, but with much weaker current and smaller capacitance, so a smaller barrier, and without microwaves. Why a weaker current was applied isn't completely clear to me. Perhaps it's just so that the microwaves wouldn't be needed to bump the system to the next energy level. So it would proceed faster, but from what I can tell, those are just technicalities. Again, you don't really need to understand that to understand why this research is so cool. In any case, this is where the quantum tunneling, in the sense I talked about at the start, occurs. The paper states these effects of escaping the zero voltage state, which earlier is clarified to be the escape from this very potential well we're talking about. The paper specifically makes a point to mention this happens at the same rate regardless of temperature. This is because something similar to this quantum effect can actually happen classically. It's called resonant activation, as you can see right here. And but the classical effects depends on temperature, right? And specifically, I point you to figure 4. The bottom graph, C, shows the resonances or dependence of the escape rate on the current at the coldest temperature right here. On graph B, however, we see something else emerge, a shoulder, as it would be called on the left side, which then evolves into an asymmetric distribution with no large peaks, right? You can kind of see something here, but it's mostly linear, um, representing the classical effect. It also is important to note that this temperature might not be what you expect it to, since the microwave frequency is the thing that's being varied. At least I'm pretty sure, because there's no mention of any Kelvin quantities in the text accompanying this figure. A little bit. Okay, I didn't include it. Okay. But yeah, it's just this that was mentioned. Oh, wait, I did include it. Yeah. There's no mention of anything in Kelvin right here. But again, I could be wrong, and it's possible they were varying the temperature in the classical sense. This is just what I was able to glean from it. So yeah. Or there might be some effect between microwave frequency and temperature that I'm not aware of. Anything is possible, right? So either way, the transition between quantum and classical is very much still an area of active research and debate, and I personally find it interesting as well because it falls into the niche of emergent behavior that I personally find fascinating every time it comes up, right? Of course, we know about decoherence, but for example, we don't really know everything about it. I don't even know where to begin with that. Okay, so that's everything I wanted to cover for this part of the video. Now let's talk about the previous year's Nobel Prize. I promise this isn't as completely out of place and out of spirit for this series as it appears to be. As you may know, from watching me last year, if you were watching me last year, the Nobel Prize in Physics in 2024 was awarded to a discovery in AI. And I had a lot of thoughts and a lot of feelings about that. And while I still believe there are points to be hashed out, and not everything about this decision was positive, I don't think that it is necessarily the Nobel Foundation or definitely not the researchers' fault. Firstly, it takes time to get a Nobel Prize. It's taking longer than ever, according to an article published in Nature, which I have linked in the description. I was not able to read it on my computer, but I was able to save this image from my phone, so I'm not sure like how that works, but hopefully you will be able to read it. As you can see, the most recent average was prizes being awarded to research from like 30 years prior in chemistry. right? Around 27 years for physics and around 26, I guess. So I guess maybe 28 for physics. Um, right? 20 around 30 years prior, right? For chemistry. And this year's was even longer actually, as we saw. The original papers were published in 1984 and 1985. That was 40 years ago. And I do, of course, understand that in prior years there was other research which needed to be highlighted, and I understand, like, I get that. And there's no doubt in my mind the fact it's taking longer is because time is in fact passing while discoveries that changed physics fundamentally are still there. And of course, I do believe every laureate has been deserving of their prize so far, including the 2024 case for physics, right? As we have seen, even just in the previous recap, physics is a really broad subject. The models and frameworks developed can be very applicable to a lot of topics, a wide variety of topics, such as neural networks. And while I do not doubt that the research selected for the 2024 Nobel Prize in physics was relevant to physics, what left a bad taste in my mouth last year that caused me to make that video talking about it was a combination of the above, right? It's taking longer than ever for research to win the Nobel Prize, which also but also the precedent it's set in like really popular science would be the best way to describe it, right? It basically said we're not doing physics anymore. We're doing AI. And I understand that's not what actually happened, but I feel like that's what a lot of people got from it. And again, I'm not trying to sound like there was research more deserving of the prize in 2024, that the outcome somehow snatched the prize from someone else. Not at all. If anything, I would say this is a step in the right direction, getting more eyes on and more funds for relevant research, which could feasibly continued in the far future in the near future is important. Like, I think that's what it should be about to some extent. But again, what rubbed me the wrong way is that it wasn't really labeled as a discovery in physics by the media. And that's in no way the foundation's fault. People just saw the big AI label and ran with it because that's what would get them more views, more clicks, right? Like, don't tell me I'm crazy for saying that, please. And I'll be honest, like, I fell for that too. I fell for the I can't really call it fear mongering, but I felt for the idea that we weren't really doing physics and physics anymore too. And granted, I was 13, but let's be so for real here. I'm 14 now. I'm not much better, if not worse. So, you know, all right, fine. So why do I care so much? Why am I dedicating a whole section in this video that is about this year and not last year to AI? Well, not to sound too preachy, but I think a very clear line must be drawn in discussions of AI between LLMs and specialized professional AI whose results are independently verified to be used in research, right? I think the fear mongering surrounding LLMs and AGI, artificial general intelligence, and all that, purely through not drawing this line, has seeped into the latter, right, of specialized AI as well. Though both do use neural networks, from what I can tell, having passively observed what the LLM flavored AI researchers are doing, this isn't really the type of research that would currently be beneficial, or I mean, the research that was highlighted for the 2024 Nobel Prize wasn't the kind of research which AI bros, for lack of a better term, would pick up on for LLM research, right? A lot of the landscape of this LLM research really consists of, and I don't know how else to put this, either hacking the LLM or beating it with a stick until it does something. like this meme. Just insert any logo you want right here, just in your mind, because that's what they're doing. And the shame really is there wasn't so much coverage of this as an achievement of humanity as much as people pointing at the big AI label on the front, right? To me, this paper demonstrates it's like this thing in physics that's inherent to the field, I think. Due to its abstract nature, it's hard to communicate what exactly the immediate applications of a finding will be to the average person's daily life, right? I talked about the applications of quantum research in the previous video, and probably the closest thing to affecting an individual's daily life in the near future was the proton arc therapy thing, which I'm getting really caught up about. I know that, but it's just it's just cool, and I feel like I can use it in a lot of examples. So leave me be, okay? But even that will only really matter if you get cancer. Don't get cancer. Like, please. I'm not responsible for that. Um, but yeah, it's hard to get a person to care when a lot of the applications of physics seem idealistic and I don't know, theoretical or practical, but in the future, in the far future. And like, sure, in the future, say quantum computers could bring about a whole new era of technology, computation, and even mathematical discoveries. But what does that mean to Mary, who likes to eat eggs for breakfast, right? Like, it's cool, but she's living on her farm and she doesn't really care, okay? And it's often only that like in that intersection, such as in biophysics or medical physics, that to speak of relatively concrete, short-ish term results is even possible. But I think what the 2024 Nobel Prize gave us is something for Mary, who maybe might consider buying OpenAI stock for fun, something to attach herself to, and a reason to care about physics. Because at the end of the day, the Nobel Foundation does as much science communication as it does prizes. That's why I think so many people hate it. And I know hate is a strong word, but that's the sentiment I was getting. And maybe I'm in a bubble, but that's the sentiment I was getting. People were saying the Nobel Foundation set a, a bad precedent, right? And to some extent, I can see that, but there's a line to be toed there between science communication and actually awarding the research that needs to be awarded. All right, that's enough. Thank you for sticking around. I hope that wasn't too rambly. Next video will be on the microboom paper I mentioned last time. It's pretty cool, so see you there. Congratulations once again to Clark, Deveray, and Martinez.